Theoretical physics, as we know it today, is built on a highly effective, yet deeply fragmented mathematical foundation. For quantum spin, physicists use matrices. For electromagnetism, differential forms. For spacetime curvature, standard tensors. While this patchwork approach works in isolated domains, it creates a massive computational bottleneck when these fields intersect, specifically in emerging disciplines like quantum information and geometric machine learning. To model a unified physical reality and to engineer artificial intelligence capable of mapping it, we cannot continue translating between incompatible languages. We require a unified mathematical foundation. The framework for this unification is mapped out in Umair Abbas's text, Geometric Structures of Modern Physics. The premise is direct. The disparate toolkits of modern physics can be entirely reconstructed from a single foundation, known as Clifford or Geometric Algebra. By centering a single foundational geometric identity, this framework connects basic multilinear algebra to complex spacetime physics and modern equivariant neural networks. To understand how this works, we have to start with a blank vector space and systematically rebuild the geometry of the universe from first principles. Adopting geometric algebra installs a structural upgrade to the underlying operating system of theoretical physics. We begin with a standard vector space. Vectors let us compute linear combinations, scaling and adding directions, but they inherently lack intrinsic spatial orientation. A single vector gives you a line, but it cannot define an oriented plane. To solve this dimensional blindness, we introduce the exterior or Grossman algebra. It provides the machinery to measure oriented areas, volumes, and higher dimensions. The core operation here is the wedge product, an algebraic representation of spanning an area. It is strictly antisymmetric, meaning u wedge v equals negative v wedge u. When you wedge two vectors together, you create a bivector. This doesn't just represent flat area, it encodes a specific direction of rotation. The exterior algebra captures this oriented area perfectly. However, it is entirely metric-free. We cannot measure exact angles or lengths. To construct an accurate model of physical reality, we inject a metric into the system. This gives us the ability to measure precise distances. We do this by defining the metric tensor. It operates as the mathematical mechanism that assigns a measurable distance to our space and allows for transformations that preserve that distance. When we combine the metric-free exterior algebra with this metric quadratic form, we deform the space into a new structure, the Clifford algebra. This combination produces the fundamental identity of geometric algebra. The geometric product uv equals the inner product u dot v plus the wedge product u wedge v. The first half represents pure parallel projection. The second half captures the orthogonal spanning area between them. The efficiency of the Clifford product lies here. It simultaneously encodes both metric projection and spatial orientation in a single computable algebraic operation. Historically, modeling continuous spatial transformations like smooth rotations using standard matrix mechanics has been cumbersome and abstract. We bypass matrices entirely using the Cartan-Dieudonné Theorem. This theorem proves that any orthogonal transformation in a space can be executed as a simple sequence of basic reflections across hyperplanes. Take a single vector. If we reflect it across a normal axis, its direction flips relative to that plane. Compose a second reflection across a second intersecting plane, and the net result is a pure rotation. This rotational operator is called a rotor. Because these rotors are generated by reflections, they inherently possess a 2-to-1 double cover topology. You have to rotate a rotor by 720 degrees to return it to its original state, meaning the spin group natively forms strictly inside the algebra itself. For decades, physicists modeled quantum spin using abstract, non-spatial column vectors and matrices. With this framework, quantum spin becomes a rigorous, visualizable geometric operation built directly into the fabric of space itself. We can scale this exact same algebra from 3D Euclidean space to Minkowski spacetime, simply by adopting the 1-3, mostly minus, metric signature required for special relativity. In traditional physics, describing relativistic quantum fields requires the Dirac equation, a structurally dense formula heavily reliant on complex arrays of gamma matrices. We replace that matrix formulation with a streamlined geometric equation consisting of the geometric derivative, the Spinor field, and the spacetime pseudoscalar. Crucially, these spinors are defined as minimal left ideals. They are not external data structures, but intrinsic elements generated by the algebra itself. Formulating quantum fields natively in spacetime geometry strips away arbitrary matrix artifacts. As a result, fundamental properties, like the continuity equation for charge conservation, emerge naturally from the geometry. This universal geometric language translates directly into the functional code of modern computational reality. In quantum information, a qubit state maps perfectly onto the geometry of three-dimensional space, using the block sphere, which naturally emerges from the algebraic spinor representation. This same translation is driving the frontier of geometric deep learning. As artificial neural networks are tasked with simulating molecules or fluid dynamics, they must be mathematically constrained to respect the physical symmetries of their data. This constraint is equivariance, a mathematical guarantee that rotating input data before analyzing yields the exact same result as analyzing first and rotating the output. Replacing standard tensors with Clifford multivectors inside the network's weights guarantees this strict equivariance across spatial manifolds. Abandoning the fragmented matrix mechanics of the 20th century in favor of geometric algebra provides a unified language. It is the essential step for building AI that inherently understands the physical laws of our universe.